Let's take a closer look at some of the numbers that we'll be working with. It's important for us to understand that there is two kinds of numbers, measured and exact. This will help us know how many sig figs. Measured numbers inherently have some error and are limited in their number of sig figs. We can know that a number is measured by looking at its units. Centimeters are length units. Length is something that we measure. And so because we see meters, we count the digits. 1, 2, 3. This number has 3 sig figs. What do we measure? We measure physical quantities. We measure length in units of meter, which is abbreviated with a lowercase m. We measure volume in units of liter, which is abbreviated with a capital L, or sometimes a sort of a lowercase cursive L. We measure mass in grams, time in seconds, and temperature in degrees Celsius. Every physical quantity has both a number and a unit. Now, sometimes the unit is too large, and so we use a prefix multiplier. On page, I believe it's 28 of your book, this is the table that you're given, which is a little bit overwhelming. Just so you know, in our class, you don't need to know all these prefixes and symbols. I think we'll be fine if we just stick with giga, mega, kilo, deci, centi, milli, micro. There will be a time and a different chemistry class where you will need to know nano, and it's possible pico. So I have a silly mnemonic device to help us remember all of these, but I suggest that for our class, since we really just need 7, figure out your own mnemonic or memorize them all. Okay, and so kilo, for example, means 1,000. And if we put kilo in front of a different a different unit, base unit, so if I had kilometers, that means the same thing as 1,000 meters. A kilometer is equal to 1,000 meters. So prefix multipliers we use to change the size of the base unit by some power of 10 to be convenient. For example, we have graduated cylinders in the lab, and they measure things in milliliters. And so let's keep in mind, the first is the prefix, the first letter you see, and the second letter you see is the base unit. So this is measured in liters. And what we have here with a milli is 1,000th of a liter is a milliliter. I could have written that this way. 1,000th of a liter is a milliliter. Centimeter, the second letter is M for meter. That's the base unit. And then centi means 100th. So we have 100th of a meter, or I could have maybe written it this way. 100th meter is a centimeter. NS, the S stands for time, is the base unit in seconds. And N stands for nano, and nano means 1 billionth, 10 to the negative 9 seconds. That has a lot of zeros. 1, 2, 3, 4, 5, 6, 7, 8, 1 seconds. And then kilograms we're going to run into a lot. So grams, grams is a mass, one of the physical quantities that we measure, and kilo means 1,000. So kilogram is 1,000 grams. The last unit that we work with is temperature. So here I have volume, length, time, mass, and temperature. We don't typically give degrees Celsius a prefix. We could, I just haven't seen it very much. Now remember, when measuring with a scale, we record all measured digits plus the one that is estimated. Let's practice that. Here we have a graduated cylinder. It measures in units of milliliters. I see the meniscus. It's right here. I'm going to get on eye level. And I'm looking at the center. I see the major divisions are 4 and 5, so the ones place, it's more than 4. And then a minor division, there are 10 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And how far up are we? 1, 2, 3, 4, and quite a bit more. And so now I'm going to estimate the distance between 0, 1, 2, 3, 4, 4.4 and 4.5, and I'm going to say it's just below the line. So I need to read between the lines to get my estimated digit. And all the digits that are significant are the ones that are measured and estimated. Measured and estimated. And so here we have 3 sig figs in this measured value. Here's another scale. Let's practice again. So we have both inches and centimeters, and typically inches are broken. The English system would have us break things in half. So here's 0 to 1 inch, and there's halfway there, half an inch. And I break this distance into half again. That's a 1/4 inch, and half again. That's 1/8 of an inch, and half again. That's a 16, a 32nd of an inch. So there's 32 divisions here. I can understand why things are broken in half. That would be an easy way to make a scale. It's easier than making maybe divisions of 10, equal divisions of 10. But it's not useful to us. So we're going to use the metric system. So we're going to focus on the centimeters. The length of this tip, this pencil, I'm going to say it is right on that 8. And so I could say 8 centimeters, but I would be wrong. And the reason that I would be wrong is because the precision that this tool offers with all these lines means there's more sig figs. So let's look at the tool to decide, are we going to go to the tenths place or carry on to the hundreds place or go to the thousands place? How far do we need to measure? Okay, so I'm just going to look at any space and say, I can see the ones are measured. That's a major division. And then in between the ones, we have the tenths. And there's lines for those, so those are minor divisions. Smaller lines, but there are lines there. And if I read between the lines on the number line, that would bring me to the hundredths. So I'm just thinking, let me write a number down here. 1, 2, 3, dot, decimal, 4, 5, 6, 7, and then some units. Okay, here's the decimal. The place to the left is the ones. The place to the right is the tenths, hundredths. So my major division is the ones. That's here. My minor division is the tenths. That's here. The estimated the estimated place is the one to the right, and that's the hundredths. So that tells me that I'm going to know the length of this pencil plus or minus 1 in that hundredths place. So we would refer to this here as the uncertainty. That's the digit, the hundredths place, where we're going to make our estimation. When measuring with a balance, you'll remember we don't need to estimate. The balance will do that for us. So we just record all the digits given. Here I have a balance that has the decimal right there. Tenths, hundredths, thousandths. It's measuring to the thousandths of the gram. And so we would call this a milligram balance. Milligram is simply to say that's the uncertain digit. That's what's being estimated. And the value here, the mass of whatever that is equal to 0.873 grams. So on a milligram balance, we're still ending up with a mass in grams. The milli is just telling us where the estimated digit was. So here we have a decigram balance. It's hard to see, but the decimal is right there. We're measuring plus or minus 1 in the tenth of a gram. That's the uncertain digit. Here we have a centigram balance. The decimal is there. The centi of a gram is the hundredth of a gram. That is the estimated digit. A milligram balance, it's almost impossible to see, but there's a decimal there. And then tenths, hundredths, thousandths. The thousandths of the gram is the place being estimated. This is called an analytical balance, and the place that is estimated is 4 places past the decimal. Hopefully we'll get into the lab and you'll get to use some of those. They're super pricey, but it's very cool. They're a very precise instrument. Okay, so the uncertain digit is the estimated digit. We still include it as a significant figure. So if I have been reported this mass, I know that the last digit I see is the estimated digit, and I now know what kind of tool was used to measure this. So tens, ones, tenths, hundredths. This must have been measured on a centigram balance, and the precision is in the centi of a gram. So precision is a funny word. There's going to be times in chemistry where we use words maybe a little differently than we use them out on the street. And precision can refer to how close a series of measurements are to one another, how reproducible they are. But it also refers to a tool's degree of precision, and that is the last digit that's significant, where the estimated digit is. For example, a decigram balance measures to the tenth of a gram. That's its degree of precision. A centigram balance measures to the hundredth, the centi of a gram. That's its degree of precision. So a centigram balance has plus or minus in the centigram place. A decigram balance varies in the tenth of the gram place. More digits to the right of the decimal. This is more precise. It has more precision. And more precision usually means it costs more too. Okay, so back to the main thing. There are 2 kinds of numbers, measured and exact. And with measured numbers, we have to count sig figs. Exact numbers don't have limited sig figs because they don't have any uncertainty. How will we know if we're working with something that has limited sig figs or no uncertainty? We look at the units. So we can count and know exactly small numbers of large things. If I was given this value, 27 students, well, I can count how many students. I can count up to 27. And so I can know with no uncertainty how many students are in the room, we would say this is an exact number. It has an unlimited number of sig figs. It is not going to limit the number of sig figs in the final answer. Now, would students always be, if we had a number with students as a unit, would that always be exact? No, probably not. If you went to a concert and there were 15,000 people, is that 15,000 an exact number, or could it be plus or minus 10? So we're knowing, and we can count and know exactly small numbers of large things. And the large things need to be discrete, like a student or a book or an egg. Exact numbers are exact, either because they are counted, and we'll know that by the units. We can count students, we can count books, we can count our chickens, or defined. And defined comes from a definition. And here's a definition. 1 foot is 12 inches. So I can take that. So if I start with 1 foot equals 12 inches. And I'm going to do some math, divide both sides by 1 foot. That's a legal operation. Anything over itself is equal to 1. I now have a relationship, 12 inches per foot, that is equal to 1, exactly. And so if I see this quantity, 12 inches per foot, I can look at those units, and then I can check the number and see, oh, that came from this definition. 1 foot is 12 inches. So that's exact. We're not going to have a lot of conversions from, for example, length to length in the English system, so between feet and inches. But we are going to do a lot with these metric prefixes, so let's take a moment for that. So 1 meter is 1,000 thousandth meters. 1 meter is equal to 1,000 thousandth meters. So right here, I have written millimeter. And thousand and thousandth cancel, because what I had here was 1,000 and then 1,000th meters, and they canceled. Oops. Okay. So 1 meter is 1,000 millimeters, because milli means 1,000th of. I divide both sides by 1 meter. Anything over itself equals 1. I now have a relationship equal to 1. That's exact. I could write it this way. 1,000 millimeters is a meter. And then when I see this value given somewhere, I check the units first. Is this measured or exact? Oh, it looks like it might be a definition. Let me look at the number. Yes, that's a definition. So the first place to look is always at the units. The units will guide you. Is this measured or exact? Derived units are a combination of other units. Mass, length, time, temperature, and sometimes volume, if measured in a graduated cylinder, are all examples of fundamental units. These are things that can be measured in one go. But sometimes you have to take several fundamental units and join them together to make a derived unit. Density is a good example of a derived unit. So density is the relationship between mass and volume of a single sample. The mass can be determined on a balance, And the balance will give us a value in grams. The volume can be determined maybe from a graduated cylinder, in milliliters. Or maybe we had to take a length times a width times a height. Length, width, height. And do a calculation. But we end up with some volume. And then when we combine the mass divided by the volume, we end up with some units that have mass per volume. These are derived units. They're derived because it required more than one measurement and then some math to get them. For volume to be a derived unit, we would need to have a dimension by a dimension by a dimension. So maybe we have a cube, and the cube has a length equal to 1.0 centimeters and a width equal to 1.0 centimeters and a height equal to 1.0 centimeters. If we were to solve for volume for that cube, we would need a formula, and the formula would be volume equals length times width times height. And for this particular situation, we would end up with a volume of 1.0 centimeters for length times 1.0 centimeters for width times 1.0 centimeters for height. 2 sig figs. 2 sig figs times 2 sig figs times 2 sig figs gives us an answer of 2 sig figs. Centimeters times centimeters times centimeters is centimeters cubed. So the volume for this cube is 1.0 centimeters cubed. And the cool thing is, if we were to fill that cubic centimeter with water, what volume of water would it require? 1.0 milliliters. 1.0 milliliters would completely fill this cube. Which brings us to a relationship that we probably need to memorize, and that is that 1 milliliter of anything, not just water, equals 1 cubic centimeter, which sometimes, maybe in a hospital setting, might be called 1 cc, cubic centimeter. So sometimes volume is a derived unit, and sometimes it's not. Meters cubed, as soon as we see that something is cubed, that's derived. That's derived. Length times width times height. But when we see liters, we know that it might have been measured directly, fundamental unit. Okay, so for sig figs and derived units, we have to stop and think. If these derived units came from things that were measured, those measured numbers have a limited number of sig figs. And so we have to consider those sig figs when we come up with the sig figs for the derived unit. I thank you for your time. And this class is going to raise some questions. So some things I said today maybe make sense and some things don't. But I hope that you'll come to a Zoom meeting and ask your questions. Because in science, it's normal with all this new material to have questions, to be a little confused. And it is okay to have questions and to be confused, but you need to ask questions. So please come to the Zoom meeting and we'll discuss this further. Thank you.